Hello, my name is Mark Dawson from the Swansea Academy of Advanced Computing. I'm going to give a brief overview of some different programming paradigms. So one description of a programming paradigm could be a style of writing or thinking about programs. It doesn't necessarily mean changing language, contrary to belief. So you can many languages today are multi-paradigm. It's more of a changing of the way that you think, although certain languages do support the greater or lesser extent certain ways of thinking. Today's going to be a whirlwind tour. It's going to be a 10,000 foot view of a number of different programming paradigms. The discussion of each is going to be very, very brief. We're going to leave more to maybe some group discussion afterwards. And hopefully some of this will be new to some of you. Otherwise, I'm sure we'll have some new stuff that crops up in the chats later. So, first looking at Wikipedia, the number of different programming paradigms is huge, frankly. So I'm going to select a few. I've selected arguably the ones that are either common or interesting. So here we've got a bunch of... This is the list from Wikipedia. We've got a bunch of imperative languages. We've got a bunch of declarative languages. We've got structured is a paradigm. We've got action, agent-oriented, and then we've got another 3 pages of other stuff. So there's quite a lot to choose from. They give this little. You might not be able to see much of that. That hasn't come out very well, but they give this little diagram as well, which shows different languages and different paradigms, and some connection or flow between them, which I thought was quite an interesting way of thinking of it. One few points I raise from this is that it doesn't. I quite like. It doesn't say declarative imperative. It says more declarative, more imperative, which I thought was interesting because. But I've gone with some classification, broadly speaking, of things into either imperative or declarative in the talk. And it also shows some languages on there that aren't too incomplete. So we'll discuss some. We'll have a look at some things that aren't. And it has the concept here of, you might not be able to say that, a named state, a named state. So the idea is that imperative paradigms have, or more likely to have, named state. And declarative programming paradigms have unnamed states, and then there's some ones in the middle that have undetermined state. So it's a nice little diagram. These are the ones that I'm going to touch on very, very briefly. So imperative for procedural object, declarative, logic, data flow, modeling, language-oriented, functional, and then very briefly event, data-driven, metaprogramming, way programming, literal programming. So they're probably, broadly speaking, the more common. So first thing, structured. What is structured? Structured programming generally arises from the structured programming theory, which broadly speaking states that combinations of subprograms, all we need is sequence, selection, or iteration to be able to build, to be able to express any computable function. Right. So this is where things like if statements started coming in. We have if statements, sequence. So one thing and then the next, and then iteration. Usually structured implies imperative. Generally, we talk about single entry, single exit, and generally structured broadly came about when they started banishing the go-to statement. Some of you might have heard of the paper, the go-to statement considered harmful, which I thought an interesting little fact I heard about that originally was that the original title was something much more benign, as in, and the editor decided that this was far too not sensationalist enough. So we started getting these X considered harmful papers. Structured programming these days usually isn't used as true structured. We use some fairly common deviations. We usually use return statements that can return from the middle of the function. which technically is a deviation from a structured program, and we use exceptions, which for the same reason you throw an exception in the middle. So the structured imperative is probably the one that we're most familiar with. We have some statements that change the state of the program. Statements are executed purely for their side effects. We also have expressions we can also have expressions. But this can introduce some global or non-global state, but generally introduces some state because we have these statements that are changing state. So that introduces problems that I think you can think of some of the other paradigms as addressing, really. Generally, imperative and structured tend to go together, although strictly they don't necessarily have to. The other broad classification of programs that's very common and covers a lot of ground is declarative programming. The most common definition of declarative programming I've heard is not imperative, but it's quite an odd one to define, really. One of the stricter definitions, I think, is probably that your expressions are referentially transparent, which means that you have expressions that so, for example, if for a function to be referentially transparent, its inputs correspond. For a given set of inputs, it has the same set of outputs. Or the idea more generally that if I have a function call, I can replace the function with its contents and have the same effect. Yes.
Do you believe declarative programming to be harder to define just because most people learn through imperative programming?
Well, I mean, I think imperative programming is easy to define because we can define a statement. Declarative programming is generally something. One way of saying it is without statements. The other way of saying it is that expressions are referentially transparent. That the consequences of having statements are fairly clear. The consequence of having statements is that I have changes of state. The consequences of not having statements are a little bit more subtle. So people tend to say things like it has no side effects, or we express logic computation, not control flow. But there are declarative programs that fall in between the gaps. So that kind of brings me on to the next point, which is the definitions. Some other definitions that you'd often see, or some consequences of expressions that are referentially transparent. So we could have no side effects. Generally declarative programming means expressing what I want to do, not how I'm going to do it. Generally variables are immutable, and these are all consequence really of referential transparency. This sometimes corresponds to mathematical logic. So some examples: database query languages, regular expressions, logic programming, functional programming, and some domain-specific languages. So that was. I'm going to quickly. They were the broad classifications under which other things are going to fall. So I'm going to dash through a few imperative paradigms. The first is procedural, which we're probably mostly familiar with. Procedural usually implies structured, although technically you can build a procedural. You could have procedural that's not structural if you start jumping around or having go-tos or exits from the middle of procedures or multiple entry procedures. So in the procedural, the program is built from procedures or subroutines or functions. They're called differently in different things. We're probably very familiar with procedural programming. You take part of your functionality, you put it into a block. That block has a name. You call the block. Generally, one of the pros of procedural. So usually we restrict state changes to within the procedure or to the return values of the procedure. So this is an interesting. As I was saying earlier, imperative programs change state. So lots of the imperative paradigms generally are addressing the fact that I can change state and making it more manageable. And procedural is a classic example of that, and restricting the changes of state to some local scope. Usually imperative. some people could say that this is a small step towards declarative, in that I'm creating some functionality, I'm bundling it away, and then I'm creating essentially some statements that appear to be defined declaratively, in that they don't have side effects in the outermost scope, and all the side effects are restricted to the innermost scope. The other paradigm I have here is object-oriented. I'm not going to spend a huge amount of time on object-oriented because it's so incredibly popular. The idea is objects encapsulate data and logic. Hopefully most people are roughly familiar with this idea. It's, broadly speaking, a sort of extension of procedural. The most popular, I would say the most popular two are class-based or prototype-based. There are others. I'm not going to go into detail. Class-based is probably the most familiar. Objects are instances of classes, and classes determine the type of the object. Prototype-based is a similar idea, but we don't have classes. Objects, this is JavaScript, can be prototype-based. An object has a related prototype, which is another object, and then you just build a tree of your objects, and each tree is derived from another object, sort of, broadly speaking. Typically imperative, typically borrows from procedural. Okay, so those are imperative. They're fairly easy. I've gone very quickly through imperative because it's the stuff we're familiar with. Declarative logic is one. Logic programming is based on formal logic. We have clauses which express either facts or rules about the problem domain, and it's usually declarative, and roughly speaking a type of constraint programming, which I could have discussed more broadly, but I'll just pick this little example. So I create some rules. I say, a bird can fly unless it's abnormal. A bird is abnormal if it's something that's abnormal is wounded, and then I state here. So these are some rules that constrain my problem domain, and then I express some facts. So John is a bird, Mary's a bird, John is wounded, and then I can ask, can John fly? That sort of stuff. You can see things like maybe solving Sudoku puzzles. I've seen expressed really succinctly in this kind of language, in that you just give the inputs, the constraints, and the outputs, and essentially it solves it for you. The problems with these are that we're not saying very much, because it's declarative. We're not saying very much about how it's done. So its optimization becomes an issue. Data flow is interesting. Operations are connected explicitly. We have a bunch of inputs and a bunch of outputs. The programming languages do this. So you can have programming languages. Generally, data flow programming languages tend to be, I would argue, visual, in that you're building trees or you're building pipelines of data flow. But a nice example that we're probably all familiar with is just Unix pipes. So here we do it. We have some data that flows from here to here to here. I have some complete nonsense written there that does nothing, but it gives the idea. Modeling, I thought, as scientists and engineers, this might be an interesting one. Again, it's an example where declarative programming is abstracting us away from the details of how this is implemented, and we say things like, we state some equations, we state some initial conditions. In this case, ignore this. That's incorrect. It's not S-English. This is Modelica. This is S-English. Language-oriented, interesting. So there's different. The example I have here is a natural language-oriented language. It looks a lot like English, and it's parsed and decided. This is a language called S-English. But more generally, language-oriented programming is the concept of me building a language specific to my problem that may or may not be too incomplete, but addresses, but in which I can express problems in a certain domain very, very quickly. So rather than me using a general purpose language for everything, I just build up my language. SQL, HTML. Why have I got these as language oriented? debatably. But the idea is I can solve specific problems very quickly in that language. I think that's a typo having those examples there. Functional. This is a really fun one. As I mentioned earlier, this is super high level. So you will see functional programming introduced more concisely than you've probably ever seen it before in one slide and a bit. So the idea is that I treat computation as valuation of mathematical functions, and if it's pure functional, I achieve the desired result by composing functions. So essentially creating functions that call, let's say, functions, apply functions. I'm not going to go into detail too much. So in pure functional programming, functionals are always referentially transparent. In certain types of functional programming, we have no control flow constructs. So we now have for loops or whiles or do or if else. It's purely yes.
It's not a bit weird because you can like a for loop is.
We have no explicit constructs.
Yeah, sure, but a for loop is referentially transparent. Like the for loop concept is referentially transparent. So you could make a function that is the for loop.
I mean, in the case of the for loop here, I mean the for loop that has a variable, a counter variable. In itself, referentially transparent, yeah, but...
Because what you could do is that you could say that for is a function that takes a number, say an upper limit, or say a condition, a value, a condition, an update statement, and a run statement, and then it is it calls itself by applying the update statement to the variable, or not the variable, but sort of
to use the Y combinator, use recursion with the Y combinator, and I mean there's recursion in so through recursion you can have loops.
Yeah, exactly.
Yeah.
But there is nothing like not transparent about recursion.
Yeah, we can have recursion, and we can have recursion with conditions. I meant, in this case, I mean an explicit part of the language that purely controls flow. So if I'm a functional programmer, I can have functions that control my flow. They happen to control the flow, but I won't have a separate syntax for if or while or a do loop. I'll have some, although
sure,
debatable.
You would sort of say that, hey, I guess it's sort of a question of what you call part of the language and what you call part of like the system library, right? Because you could have like a language library that has a function that's called repeat until, right?
Yes. Yeah. Yes.
And that's
Yes. I mean, I can construct things that behave exactly like for loops, or while, or do, or whatever else, very easily. And depending, I mean, you look at the right, supposedly, languages aren't, unless you're really looking for a single paradigm language, you can have things that are not single paradigm, but you can look at languages that are supposedly functional that would have a for, or while, or do, or whatever else.
Yeah, sure. It just feels like a weird arbitrary restriction. You're basically saying that, like, this function that has the behavior of a for loop is sort of forbidden.
Yes, and it's not. It's often the case that people avoid, or that languages that are functional don't have the keyword for.
Yeah, sure.
Yeah, so it's not. Yeah. And functional are supposedly famous for being flexible, so I'm not saying that I can't construct these things either. And often no mutable data, or no mutable types, no mutable variables. Functional, so that's functional. I got a silly example of functional. I'm not going to go into 1,000 different things that we could do, but an example of to illustrate what composition is if I have two functions, one that takes an integer returns boolean, and one even that takes an integer returns boolean, even or not even, and a not function takes boolean returns boolean. I could achieve the odd function by function composition rather than the way that I'm maybe more used to, which is create a function that within it calls the two functions. Yeah. So basically, I'm building a function out of two different functions. Just to extend that concept a little bit, we've got concatenative languages, where the idea is that the idea generally is that I have some sort of stack. These are very uncommon. The only real useful example I could find is PostgreSQL. But the idea is here that I have arguments that are pushed onto a stack, and then the function pulls the two arguments from the stack. So if I wanted to do this kind of thing, I could write it as this, which is the composition of the three functions. So the arguments would get passed down the tree. So I thought that was an interesting, possibly could be thought of an extension of a similar concept. Some more stuff. I've got event-driven, data-driven, which is quite interesting in that it's used. So the idea here is flow is determined by events or data matching a criteria. I've lumped them together. They're generally not lumped together. So in data-driven, I describe the data to be matched and processing required, rather than defining the sequence of events. So is that? Yes. So that's data-driven. So SED, awk are kind of good examples of this, or anything that looks at the data and decides and does some maybe branching or forking or control flow based on the what's in the data. Event-driven, GUI programming tends to be very can be thought of as an event-driven paradigm. JavaScript is very good for event-driven programming. It's one of the reasons that Node got so popular. Meta-programming, programs treat programs as data. Not much to be said there. So we can read, generate, analyze, or transform programs, or it can transform itself. Lots of different sub-classifications of meta-programming. I won't go into those. Array, this is here purely because we're scientists, so this stuff's interesting to us. So we transparently handle scalar or vector, scalars, vectors and matrices in the same way. So we apply the same operations. MATLAB, I mean, this is, to me, not really, I don't think of it as a paradigm, but it's listed. And Wikipedia lists it as a paradigm, so I thought it was interesting one to go into. Literate, again, I put this in here because there was some discussion about it last time, clearly. So the idea is the program gives an explanation of the program's logic in a lateral language, and it contains some executable chunks, so it contains some macros, it contains something that could be turned into code. And then the code can be viewed in two ways. One is my woven, it's called, interpretation, which is the one that logically follows the flow of thought for me. And the other is the tangled interpretation, which is that this code is taken, turned into something that can be run by the machine, possibly reordered, possibly done in a different way.
So it's basically any language versus this machine code?
Human language, you mean?
No, just programming language, right? Because programmers think in sort of like, C programs are easy to read for me, so it's...
Yeah. I mean, the idea of this really, I think, is just to take high level to its logical extreme, which is, right, I'm just going to write what I... Yeah.
I mean, not all C syntax is easy to
Yeah, I've seen some of your code, Jonas. Easy to read. So that's it really. I'm just literally run through a couple of different types of programming paradigms, and the conclusion, I guess, is that we can think of programming in different ways. We don't necessarily have to change our language, and I like to think that exploring different paradigms and different ways of thinking can make us better programmers. So thanks for listening.